Hey there, so this is a video on 12.3, which is on similarity mappings, and similar shapes are shapes that are the same shape but not necessarily the same size. So if you look at the two pictures that you can see here with the heart, so we've got a smaller one and a bigger one, and those hearts are the exact same shape but just different sizes. Same with the pocket knife. That small pocket knife, it looks like those blades are tucked in, but they still look like the same knife. And one way that you can kind of think about this is with a copy machine. So if you were to use a copy machine and stick a picture with the copy machine to make a copy, you could either make a copy of the exact same shape and size, and that's usually what we do, in which case we would say we have a scale factor of 1. When you multiply anything times 1, it just stays the same. Or you could have the copy machine enlarge it by a factor, or you could have it shrink. Well, anytime you have a copy machine enlarge something or shrink it, it's creating two similar figures, so same shape but just different size. So these two examples here, we've got similar hearts and then the similar pocket knife. So same shape, but not necessarily the same size. So another way to think of it besides the copy machine might be by using a flashlight. This is a great example to use with kids because you could actually do this in the classroom. So if you think about what would happen if you were in a dark room and you put your hand out in front of you and you shone a flashlight on your hand, well, you would see your hand on the wall. You know, I'm sure you've done this before where you make shadow puppets. Your hand, your exact same hand is on the wall, so same shape, but your hand's usually bigger. So you're creating a similar figure. So you've got a smaller hand and a bigger hand, which are similar figures. So the way that we draw this in math, you can check out this picture down here. We say this point O down here, we're going to call this the projection point. And that's like your flashlight. So your projection point is where your flashlight is, okay? And you've got two figures here. So the important part in this lesson is trying to identify what part's the original and then what part, what figure is, we call it the image or the after, like what happens to the original figure after you change it by enlarging it or reducing it. And the way that you tell is you just look at the letters on the shape. So if it uses regular letters like A, B, C, and D, this is what we call our original, which is our image, or I'm sorry, not image, we call it original. So that's our original figure, or I meant to say before, okay? So before we do anything, the original. And then if you look at the letters on the red shape, you see they all have apostrophes. We can call these prime, so A prime, B prime, C prime, D prime. This is what we call the image, or the after. So what happens after you shine a flashlight on the green figure. So just pay attention to how the letters are drawn, and the ones with the apostrophe will always be your after or your image. And we can actually write a similarity statement with these two figures, and we can say that A, B, C, D is similar to, so similar, the symbol for that is a squiggly line. It's similar to A prime, B prime, C prime, and D prime. And just like with congruent statements, you can actually match up the letters with each other. So A corresponds to A prime, so you can see on the picture, those match up with each other. B corresponds to B prime, C corresponds to C prime, and D corresponds to D prime. So order in which you write this matters. So the flashlight is one way that you can think of that in addition to the copy machine. So let's talk about the different types of scaling we can do. So we can either, let me just erase this so we can see here, we can do a couple of things with the original figure. We can reduce the original figure, so we can do a reduction, okay? And whenever we do a reduction, we can say that the scale factor is less than 1. Okay, what does that mean? So let's take a look at this picture. So check out the letters and see if you can identify what's the original and what's the image. Okay, this green one has regular letters, so we're going to say this is the original, and this one down here is the image, because we see those apostrophes near all those, next to all those letters. So if the original is bigger, then that means we have a reduction going on. So it's getting smaller, it's being reduced. And anytime it's getting smaller, we say it's a reduction. And the scale factor is less than 1. So what does that mean? In this statement right here, it says that figure ABCD is reduced by a factor of 1/3. What that means is that every side length on the image is 1/3 of the length of the original. So for example, let's say, let's see, I'll use a different color. Let's say, I know we've got some curves here, so that wouldn't make as much sense. But let's say this length right here, we'll say that's 9. Okay, that corresponds to this length, A prime D prime over here. So if we wanted to know that side length, all we would have to do is 1/3 times 9. So 1/3 of 9, of in math means times, and we would get 3. And so this side length would be 3. And so every single side length is reduced by a factor of 1/3. So we multiply by 1/3. Okay, so let's come over to the right. So this is a different example where we've got an enlargement. So check out the figures and see if you can figure out which one's the original and which one's the image. So this figure right here we're going to say is the original because we have regular letters, and this one is the image. Okay, and so in this case our original is getting bigger. We have an enlargement, and anytime we have an enlargement, it means the scale factor is greater than 1. So if we look at the statement here, it says that figure ZXW is enlarged by a scale factor of 3. So what that means is if we have a side length, okay, so if we have a side length on the original, so you're going to take the original side length, and every single side length on the original, you're going to multiply those by 3, and that's going to give you the image. So for example, let's say this side length right here, let's say that was 4. What you would do is you would multiply by 3 and you would get 12, and that would give you the length over there on the image shape. So I'm just going to scroll down here. In terms of content standards, let's just talk real quick about where you're going to see this teaching wise. So I would say in this letter right, or this number right here, this 8, this tells you that in 8th grade, students do full similarity. So what we're doing right now, similarity, help if I can spell, similarity, there we go. So what we're doing right now, I would say is consistent with what 8th graders would probably do, but I would definitely say in grades 3 through 5, they're going to begin. So students are going to begin with proportionality. And we'll talk about what proportionality is in a little bit. But it has to do with you're setting the stage there in grades 3 through 5 for similarity. Okay, so let's talk about, we talked about enlarging, we talked about reducing. Let's talk about what happens when the shape is flipped. So check out this example with the flag. So if you look at these flags, you can see the green flag is going to be our original, the red flag is going to be the image. And so let me just write that down. So we've got, I'm going to call this original, and then we'll call this image. And it looks like it was reduced, so it looks like the green flag was shrunk, and then it was also flipped around. So we know that when it shrinks or reduces, we know it looks like the scale factor is less than 1. Okay, but what makes it flip? So flipping it is caused when we have a negative scale factor. And one way that you can think of this is if you look at this projection point, point O here, and if you imagine for a minute that this was the origin on a coordinate grid, so an XY grid here. And you looked at this green flag, and let's say this point at the very top of the green flag, let's say for a minute, let's just kind of make some dashes here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, let's say that this was -7, +7. So to the left 7, up 7 is how you got to this point. If you were to multiply both of those numbers by a -1, what would happen? So -7 times -1 is 7, and 7 times -1 is -7. They would flip around. Well, what does that point look like? It means you would go +7 in the right direction and down here. Now we're not going quite as far, so it's probably not 7. We also have to take into account that we also have a scale factor of less than 1, so which is why this red flag is a little bit closer to the origin. But I'm just using this as an example. You can see that when you multiply these numbers by -1, it changes their position by flipping them across the y-axis. So they're moving horizontally, and then they're also moving vertically, and it causes the object to flip. Okay, so we've got a couple of things going on. So you can reduce, you can enlarge, and then you can also flip it. So let's check out example 1. So let's look at these figures, and the first thing I want you to do is try to figure out, well, I guess we don't have to figure it out, it tells us. So which one's the image, which one's the figure? So this is the original. So ask yourself, is it being reduced, okay, or enlarged? So in this case, it looks like it's being reduced. And is it being flipped? It doesn't look like it's being flipped to me, so not flipped. So since it's not flipped, although this would be hard to tell since they're both rectangles, since it's not flipped, I'm going to assume that there's a positive scale factor, so it eliminates the negative scale factor, C and D. And based on the fact that it's being reduced, we know that the scale factor is going to be less than 1. So that causes us to choose option B. So it looks like B is a good answer for that one. Now for the second example, so we've got our original figure. So this is our original. Okay, it looks like we've got a situation where we're flipping. Oh, and you know what? Let me actually mention this real quick. So I did say with the first example with the rectangles, it's hard to tell if it's flipped. One way that you can actually tell, I should have mentioned this, that it's not flipped is if you look at these little dashed lines, it tells you, this is what tells you it's not flipped, because on this figure you can kind of see how the dashed lines are connected to the O here, and they're on either side of the projection point. Okay, just like same as if we scroll up here, see how these flags are on opposite sides of this projection point in the middle. So that tells us that there's a flipping happening. So with example 1 in the second box, we know that there's a flipped. We know that they're being flipped, so that tells us there's a negative scale factor, so it narrows down our options between C and D. And then it also looks like it's reduced. The original green is getting smaller, so we know that the scale factor is going to be less than 1. So that means it's going to be option C. So X is going to be between -1 and 0. Okay. So let's kind of scroll down here. Let's talk about the properties for similar figures and similar polygons. So similar figures, we said, were the same shape, but not necessarily the same size. I guess the better definition, or the more specific definition for that, would be they're similar if and only if there exists a similarity mapping of one figure to the other. And a mapping just means that you can take one point. Okay, so for instance, I know this is small here, but this is D and this is D prime. Every single point on the figure, okay, the original figure, maps, or you could say corresponds to a point on the other figure. Okay, and two polygons are similar. So let's talk about polygons for a minute. So those hearts, that beginning example I gave you, or those pocket knife, example, those wouldn't be polygons because there were curves on those. But remember that polygons are just closed figures that have line segments as sides. And we're gonna, I would highlight this box here. So there's two rules for polygons to be similar. Their corresponding angles are congruent. Congruent means equals, and that's the sign for congruent, so they're the same. And the lengths of the corresponding sides are the exact same. So for example, let's say you had two triangles. So triangle 1 and triangle 2. Okay, the angles would all have to be the same. So let's say this is 60, 60, 60, 60, 60, 60. So we say, okay, all the corresponding angles, and I'm going to actually name them too. Let's say this is ABC and A prime, B prime, C prime. So these angles are the same, these angles are the same, and these angles are the same. So that allows us to check that first bullet there. Number 2, the lengths of their corresponding sides have the same ratio. So let me fill in some lengths of sides. So let's say this is 3 and this is 12. And let's say this is, well, I'm giving you an equilateral triangle here. So they would all have to be 3 and all have to be 12. But if you look at the sides, the relationship here, 3 times 4 gives us 12, 3 times 4 gives us 12, and 3 times 4 gives us 12, okay? That's an example with equilateral triangles where they're all the same. All the sides are the exact same. Let's take a look at this next example where we've got 2 triangles, but they're not equilateral triangles. So we're told here, because of the similarity statement, that triangle ABC is similar to DEF. Okay, so one thing you could do if you wanted to is you could match up the angles and match up the different sides. I'm going to use different colors. So it looks like A corresponds with D, and B corresponds to E, and C corresponds to F. Okay, so we're not using the primes here, we're using different letters, which is good. It gives us another type of example. Find the side lengths of AB, so we're looking for this right here, and we're also looking for EF, so we're looking for this side length. So what I would do at this point is I would match up the corresponding sides. So side 21 corresponds to 7. I can see that because I labeled the different letters with different colors and they look like they're the same. The other way to see it would be side AC if we look at the similarity statement. So here's A and here's C. That corresponds to D, E, because they're both, A is the first letter, C is the third, D is the first letter, F is the third. So you can match up the letters like that. So 21 goes to 7, and what we're going to do is we're going to write a fraction. So 21 goes with 7, okay? And I'm going to label this. 21 is the big triangle, 7 is the small triangle. Okay, and I'm going to make a proportion. So I'm going to say 21 is to 7, and then I'm going to take 2 of the other sides. The question mark, the unknown, goes with 5. Let's call this X. So X is to 5, and I set up a proportion. X is the big, and 5 is the small. So you want to keep everything consistent here. And then what we're going to do is we're going to cross multiply. So we're going to say 21 times 5 equals 7 times X. So we get 189 equals, oh, nope, that's not right. We're going to get 21 times 5, we get 105 is equal to 7X. Okay, and then we divide both sides by 7, and we get 105 divided by 7, we get 15. Okay, so it looks like our answer is 15 there. Next, I want to find the other question mark. So I'm going to come and I'm just going to erase this here, and I'm going to set up the same proportion. I'm going to start by setting up the same fraction. So 21 is to 7 equals, but then I'm going to try to incorporate this other side, EF. I'm going to call this Y. And the way I'm going to do that is I'm going to take this 27, side BC corresponds to EF. So 21 is to 7 as 27 is to Y. Okay, let me actually just erase this. I feel like it's getting a little messy, and I'll do that again here. So let me change that. So we've got 21 is to 7 as 27 is to Y. You always want to go in the same direction. So if you're going big to small, you have to be consistent and do that both times. And then you're going to cross multiply. So 21 times Y equals 27 times 7. And if you solve that, you end up getting Y is equal to 9. So y is equal to 9. And one thing I want to mention, they should be really simple and easy to check your answers. So when you're all done, okay, and I would pause the video if you want to write this because I'm going to erase all this. So when you're all done, okay, I'm going to come back and I'm going to label the sides, and then you can use your calculator to divide and make sure that you get the same thing. So we found that side AB was 15, and we found that side EF was 9. And so what we can do is we can make fractions. So 21 is to 7. That should be the same as 15 over 5. That should be the same as 27 over 9. Okay. 21 divided by 7 is 3, 15 divided by 5 is 3, and 27 divided by 9 is 3. So that checks out. That tells us we did the same thing. So there should be the same relationship. So we can say that there's a scale factor of either 3 or 1/3 depending on which way we're going. Okay, so let's look at example 3. So compare the following square and rectangle. Which condition for similarity do they satisfy? Are they similar? So let's write down. So we need congruent angles. So let's first ask, we're going to say question mark. So let's look at that. So we're looking at the square and rectangle. Are there congruent rectangles? Well, all of their, I'm sorry, not rectangles, are there congruent angles? All of the angles are 90 degrees. So we say yes. It satisfies that first condition, okay? The second condition, which is proportional sides, let's look at that. So we've got the side lengths here, and let's match them up, okay? Let's look at this first relationship. This side on the square is 2, and the rectangle is also 2. So that has a scale factor of 1. 2 times 1 is 2. Now over here, if I were to go from 2 to 3, that has a scale factor of 1.5. 2 times 1.5 is 3. These scale factors are not the same. So I'm going to say no, they don't have proportional sides because the scale factors are not the same. So we would say not similar. And we can just look at those and see that they're not the same shape. So, but it's good to go through these steps and decide using the two conditions that we talked about. Let's look at number 2. So now we're going to compare the rectangle and the parallelogram. So I'm going to erase this. And let's look at both of the conditions. So one is congruent angles. Okay. The angles on the rectangle are right angles, and it looks like these angles are not right angles. So I'm going to say no, the angles are not congruent. So these two are automatically not similar. But let's check out the sides. So proportional sides. Let's see if they have proportional sides. So I'm going to match up the sides. And it looks like, so 3, they're both the same. So the scale factor is 1 and the scale factor is 1. So I'm going to say yes, the sides are proportional since we're multiplying by the same number each time, each pair of sides. So it satisfied the proportional sides but not the congruent angles. So we still say that these are not similar because it has to satisfy both conditions in order to be similar. Okay, so let's talk more specifically about triangles. So we talked about the two conditions that need to be in place in order for polygons to be similar. With triangles, there's some properties that we can use to help us determine if triangles are similar if we don't have all of the information. So let's take a look at this example 4, the first one, the first box, and then we'll come back to these properties and I'll talk about them. Like if you look at the two triangles here, so you've got a triangle right here on the left, and then you've got another triangle here on the right. And we're trying to figure out, are these similar? Well, I don't know all of the angles. I know that they both have a right angle, great. And I don't know the lengths of the sides. So I can't use those two properties that I did above to determine if they're similar. But there are some properties that I can use to determine if they're similar since we have triangles. One is called the angle-angle similarity property, and that's this first one. And what that says is that if two of the angles of one triangle are congruent to two of the angles of the other, then the two triangles are similar. So if you look at this first example, they both have right angles. Okay, so that's one pair of congruent angles. We would need another. And the other is going to come from these angles right here. These are congruent because they're vertical angles. So you're going to say yes, triangle, we'll call it HKA, is similar to triangle HEG. And I knew the order to go in because I started with H and I went to the angle that was not right, K, and then to the right angle, A. And so I made sure to do the same pattern over here. So I started at H and then I went to E and then I went to G. Okay, it doesn't matter the order, you just have to be consistent. So let's go and let's look at the next example. So in the next example, it looks like I've got a 30-degree angle matches up with a 30-degree angle. Okay. And now the 95 and 55 don't obviously match up, but what we can do is we know that all angles, so angles in the triangle, need to add up to 180. So for this first triangle, we've got 30 plus 95, so we can add those together and we get 125 degrees. Okay, and then if we subtract that from 80, so we get 180 minus 125, we end up getting 55. So we know that this angle C is 55 degrees. Okay, that does give us two matching angles. So we have 55 and 55 here. So you can use the property of angles adding up to 180 to find missing angles to see if you've got matching pairs. So we're going to say yes, these are similar because of angle-angle theorem. So this next example, we don't have angle measures, and I'm going to just kind of come up here. We talked about this one property, angle-angle. The other one, so property number 2, would be side, 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 and that says if the corresponding sides of two triangles are proportional, so not necessarily the same, but proportional, then we can say they're similar. So let's look at this first example and see if they're proportional. So if we make a proportion, it means we have two fractions that are equal to each other. So the first thing that we have to do is we have to look at these triangles and we have to try to see if we can match up the sides. So I'm just going to guess, and this would be a good spot, pause the video and try it on your own. So I'm going to guess here that this 35 is going to go with the 24, okay? And this, I'm just eyeballing it and I'm looking at these two sides thinking, okay, those sides look like they're about the same if we had flipped this first triangle around. And it looks like 48 would correspond to the 32. It looks like 50 would go to the 35. So at this point, I'm going to make some fractions. So I'm going to say 35, actually let me come up here so I have more room. So I'm going to say 35 is to 24. Is that the same as 48 over 32? Is that the same as 50 over 35? And what you could do is you could take your calculator, you could divide those, okay, and see if they're the exact same. So 35 over 24, we get 1.45. 48 over 32 is 1.5. We can see that those numbers are not the same. They're really close, which is why these figures do look similar, because the scale factors are really, really close, but they're not the same. So you're going to say no, not similar. And we weren't given angles, so we're not even going to talk about the angle-angle property. So we're just looking at the sides. Okay, so for this next figure, it looks like we've got this side here matches up with this side. This side looks like it matches up with that side. One thing I do know is if we have two sides that they're the same, these are called isosceles triangles. And anytime you have an isosceles triangle, let me just draw a picture, two of the sides are the same, these angles are also the same. So the angles opposite of the congruent sides are also the same. So I could say that this angle is the same as this one, and this angle is the same as this angle. Does that help us though? if we look up above, so let's look at our two properties. We've got angle, angle, which means the angles, we've got two pairs of angles are congruent, the exact same, or side, 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 where we have all sides proportional. We don't have either here. So I know that these two angles within this triangle on the left are the same, but I don't know that they're the same as these angles over here. So because of that, I can't use angle, angle, and then I don't know the lengths of the sides, so I can't say that we have side, side, side going on. And they very much could be similar, we just don't have enough information. So I'm going to write not enough info. Okay, so let's look at this last one. So, well, not last one, the third one. So I'm going to compare sides again. So I'm going to say this 33 looks like it goes with the 22. This 33 goes with 22, and it looks like 21 goes with 14. So I'm going to make some fractions. So 21, 14, 33 over 22, and then these are the same. Are these the same fractions? Well, 21 divided by 14 is 1.5, and then this is also 1.5. So we say yes, they're similar because of side, side, side similarity property. All right, and lastly, let's look at this last one. So this is an interesting problem. You're going to see this in your homework. It looks to me like it's easy to look at a problem like this and see only one triangle, but we actually have two, and I'm going to use different colors to highlight where these triangles are. So we've got that smaller triangle and then this bigger one. So the bigger triangle has some overlapping sides. So it looks like this is M, and this is T, and this is S, and this is R. Okay, so what do we know? We know that angle M is the same as angle N because that's what these symbols mean. So angle M is congruent to angle N, okay? We need two congruent angle pairs in order for us to say they're similar. The other angle that we know is similar is up here. Angle R is the same angle on both triangles. So angle R is obviously congruent to itself. So we're going to say yes, they are similar because of angle-angle theorem. So the next part, and this is the last part of the notes, is just to talk about how similarity affects area and volume. So we're first going to look at area. So take a look at these two rectangles, and this first rectangle is 4 by 2, so this is 2 and this is 4, and the second rectangle is 12 by 6. And you could first ask yourself, okay, well, are these two rectangles, are they similar? Let's go through the properties. So the angles, let's check, are angles the same? So angles congruent. Well, both of them have right angles in every corner, so we're going to say yes. Okay, and are the sides proportional? Well, 2 goes with 6, so 2 times 3 is 6, and 4 goes with 12. 4 times 3 is 12, so since we're multiplying both by 3, same scale factor in both cases, we're going to say yes, the sides are proportional. So the rectangles are similar, so we know that. Okay, now let's look at the areas. So I'm going to erase this so you can get some more room. So if this is 4 by 2, 4 times 2 has an area of 8. Okay, if this is 12 by 6, 12 times 6 is 72, so this has an area of 72. So if the sides, I'm just going to write down, if the sides differ, so I'm just going to write down the scale factor. The sides have a scale factor of 3. Okay, let's look at how the areas compare. So how does 72 compare to 8? So just get a little bit more room. So this is 8 and this is 72. Okay, so 8 times 9 is 72. So the sides are times 3. The area differs by 9. So what's the relationship of 3 and 9? Well, if you square 3, you end up getting 9, and that's what this box basically says, is anytime you have a plane figure similar to another of a factor of k, so we'll consider this k is 3, then the area is going to change by k squared. So whatever the original scale factor is, we can square that number, and that'll tell us how much the area is going to change by. So let's use that property and do example 5. So number 1 says if the scale factor from a small photograph, so I'm going to draw a picture here. So if we have a small photograph, okay, here's our small photo, it's enlarged by a factor of 3. So that means, let's say, I'm just going to say times 3. Each of the lengths are 3 times bigger in the big photograph. And the small photograph is 15 square inches. So the scale factor is 3. And the area here on this one is 15 inches squared. What is the area on the large photograph? Well, if the original scale factor is 3, then the area is just going to change by 3 squared, or 9. So we're going to take 15 and we're going to multiply that by 9, and that's going to give us 135 square inches. And that's the area of the bigger photograph. Okay. Let's look at the second example. So if the surface area, so we're still dealing with area, of a box is 52 square centimeters. So I'm just going to draw a box. Okay, if the area, so the surface area on this box is 52 square centimeters, and the scale factor from the box to a larger box is 2, so let's draw a larger box. So the scale factor is 2. What is the surface area of the large box? So if the surface, or the scale factor is 2, what we're going to do is we're going to square that, which gives us 4, and that tells us that the areas are going to change by a factor of 4. So 52 times 4 is equal to 208 square centimeters, and that's going to be the surface area of the bigger box. Okay, and then last but not least, so we've got a large globe. So I'm just going to draw a picture. We've got a large globe here, and it says the scale factor of a large globe to a small globe is 1/2. So it's being reduced. The scale factor is 1/2. And the large globe has a surface area of 76 square feet. What is the surface area of the small globe? So if the scale factor is 1/2, what we're going to do is we're going to square it. So 1/2 squared is 1/2 times 1/2, or 1/4. So it means the surface area is going to be 1/4 as big. So we're going to take 76 times 1/4, and that's going to give us 19. So the surface area here on the smaller globe is going to be 19 square feet. Okay. So just like surface area is impacted by scale factor, so is volume. So let's take a look at these two cubes that we have here. Well, they're not cubes, they're rectangular prisms. So this first cube looks like it's 3 by 2 by 2, and then this one looks like it's 6 by 4 by 4. So if we look at the scale factor of the sides, so if we match up all the sides, it looks like there's a scale factor of 2, because we're taking each of the small sides and multiplying it by 2. Let's look at the volumes. So the volume of the small box, we're going to do the area of the base times the height. So the area of the base is 3 times 2 times the height of 2. So the volume is 3 times 2 times 2, or 12. Okay. The volume of this next one is 6 times 4 times 4, so 6 times 4 times 4, and we end up getting 96. Well, how does 12 compare to 96? 12 times 8 is 96. So the scale factors are times 2. The volume changes by 8. what is this relationship between 2 and 8? Well, 2 times 2 times 2, or 2 cubed, is 8. So whatever the scale factor is, you're just going to cube it, and that tells you how the volume changes. Okay, and that's what this box says here. So let's take that and use that property with example 6. So for the first one, we have a box that is 54 cubic centimeters. So I'll just draw a picture. So we've got a box, and let's say the volume is 54 cubic centimeters, and the scale factor from this box to a smaller one, so it's being reduced, scale factor is 1/3, so it's being reduced by a factor of 1/3. Okay, what is the volume of the smaller box? So we're going to take the scale factor and we're going to cube it. So the scale factor is 1/3. Whoop. And we're going to cube it, which means we're going to do 1/3 times 1/3 times 1/3, and that gives us 1/27. So we're going to take the original volume, which is 54, and we're going to multiply that by 1/27, and we end up getting 2 cubic centimeters. So the original volume is 54 cubic centimeters, and the ending volume of the smaller figure is 2 cubic centimeters. So the answer is 2 cubic centimeters there. For number 2, so we've got a globe. Let me just erase this. So we've got a globe, and it's being enlarged. So the scale factor going from one to the other is 4, so this is 4 times as big, and the small globe has a volume of 62 cubic feet. Okay, so this is a three-dimensional, this is a sphere here. Okay, we want to know what is the volume of the bigger one. So if the scale factor is 4, then we're going to take 4 and we're going to cube it. So 4 times 4 times 4, and that gives us 64. So it means the volume is going to be 64 times as big. So 62 times 64 gives us 3,968 cubic feet. Okay, so I hope that helps. Make sure you let me know if you have any questions.